In this lesson, we will learn the trapezoidal method. It is a simple and powerful numerical integration technique used to estimate the area under a curve. When exact integration is difficult, impossible, or when we only have measured data points. We will start from the basic idea. Derive the formula. Solve an example step by step. Then discuss accuracy, limitations, and real applications in engineering, computer science, artificial intelligence, and data science. In calculus, we often find area using exact integration. But in real engineering and scientific problems, the function may be complicated. The antiderivative may not exist in a simple form, or the data may come directly from sensors. For example, a vehicle speed sensor gives speed at separate time instants. To estimate distance traveled, we need the area under the speed-time graph. That is where numerical integration becomes useful. The trapezoidal method has a very visual meaning. Suppose we want the area under a curve from A to B. Instead of using the curved top exactly, we join the two endpoints by a straight line. This creates a trapezoid. The area of this trapezoid becomes an approximation to the actual curved area. Now let us derive the formula. The two parallel vertical sides have lengths f of A and f of B. The distance between them is h, where h equals b minus a. The area of a trapezoid is 1/2 into the sum of the parallel sides into the distance between them. Therefore, the integral from a to b is approximately h by 2 into f of A plus f of b. For a better approximation, we divide the interval into n equal parts. Each small interval forms one trapezoid. Adding all these trapezoids gives the composite trapezoidal rule. The first and last ordinates appear once. All middle ordinates appear twice. Because each middle height is shared by two neighboring trapezoids. The procedure is straightforward. Choose A and B. Choose n. Compute h. Generate the points. Evaluate the function values, and substitute into the composite formula. A useful practical rule is this. If the answer changes noticeably when h is made smaller, the first answer was not accurate enough. Let us solve a complete example. We estimate the integral of 1 divided by 1 plus x squared from 0 to 1. Using 4 equal subintervals. The step size is 0.25. The x values are 0, 0.25, 0.5, 0.75, and 1. Now we calculate y equals f of x at each point. Substituting these values into the trapezoidal formula gives t4 equal to 0.78. 2794. Graphically, the method uses 4 trapezoids to approximate the area under the curve. Since this curve is smooth, the approximation is already quite close. The exact integral is tangent inverse of x from 0 to 1, which is pi by 4. The absolute error here is about 0.0026. For a smooth function, the theoretical error contains h squared and the second derivative. The second derivative measures curvature. This means the trapezoidal method is very good for nearly straight curves. But it needs smaller intervals when the curve bends sharply. The trapezoidal method is simple. But it is not magic. It can be inaccurate for highly curved functions, discontinuities, noisy data, unequal spacing, or sharp peaks. In practice, we should check the answer by repeating the calculation with a smaller step size. If the answer stabilizes, our confidence increases. The trapezoidal method appears wherever accumulated quantity is needed from sample data. Mechanical engineers estimate work from force displacement data. Civil engineers estimate earthwork volume. Electrical engineers calculate energy from power signals. It is also used in thermal systems, chemical processes, data science dashboards, machine learning experiments, simulations, robotics, and sensor-based computer systems. A very common example is vehicle distance estimation. If we know speed at discrete times, we estimate the distance by calculating the area under the speed-time curve. The program logic is short. Read the limits and number of subintervals. Compute h. Add the first and last function values once. Add the middle values twice. Then multiply the total by h by 2. The same logic can be written in MATLAB, Python, C, Java, or even a spreadsheet. Always check that n is positive and that the final answer is printed with enough precision. To summarize, the trapezoidal method estimates integration by replacing a curved area with trapezoids. The composite rule adds many trapezoids for better accuracy. It is easy to implement, useful for experimental data, and widely used in engineering, data science, machine learning, and computer simulations. The key is to check accuracy by using a sufficiently small step size.